Okay, we've talked about the basic building blocks of nucleotides, which are the basic building blocks of nucleic acids, and we saw that a nucleotide was an assembly of a base, an organic base, a purine or a pyrimidine, a sugar, which could be ribose or 2-deoxyribose, and phosphate. Now we're going to talk about how these things are assembled into nucleic acids. It's pretty uniform the way this is done. You see that these are polymers essentially put together by phosphodiester bonds. You see 3', 5' phosphodiester bonds in there. And this is set up where there's, let me blow this up, make it a little bigger. Hopefully you'll be able to see this better. By convention, we write starting from the what we call the 5' end. If you remember, the ribose or deoxyribose is a 5-carbon sugar, and it is in this ring structure, and the carbon atoms are numbered from, well, this is 1, where I have you should see the cursor here, where the beta N glycosidic linkage is located. That's carbon 1. Next one over is carbon 2, and then you see carbon 3 is labeled here, carbon 4 and carbon 5. The basic nucleotide itself has just the one phosphate there. You see there's another phosphate attached on here. The way they put these together, though, you're going to start with the 5' end, and then there's going to be another nucleotide attached to the 3' end of that one, so that you've got a 3'. The first nucleic acid is attached to the second nucleic acid via 3' ester linkage. You see it's 3' to 5'. And you see, here's where we're going to get into some complexity in these things, because nucleic acids are very complex, but you think about it, it's actually pretty simple. The polymer part really is phosphate and sugar, just one after the other, but then you see there's the beta and glycosidic linkage, which varies considerably. So, and it's the sequence of bases is what gives the nucleic acid its information carrying capabilities. And there's only 4 bases in DNA and only 4 in RNA, and you remember that the RNA uses uracil, whereas DNA uses thymine, which is going to have a methyl group over here. And these things are strung together starting from the 5' end, 5', then that one, the first base, the first nucleotide gets attached to a phosphate, the 5' phosphate from the next one, and then the 5' phosphate, the next one, the 3', 5', and so on. So we typically write from the 5' end of the polynucleotide chain from the nucleic acid. There are a couple of cases where we're going to deviate from that because of the peculiarities of DNA, and you'll see what I mean. That's the basic structure. So, having said that, we see that nucleic acids are polymers of many nucleotides, and this can run from anywhere from transfer RNAs, which are like in the 70 plus nucleotides, on up to the great big DNA molecules in the genome, which run into the, well, in some cases, millions of bases, maybe even billions. They're really big molecules, so they're very large molecules. The sequence of bases is unique. It's called their primary structure. So just like proteins, nucleic acids have a primary structure, and they actually have a secondary and tertiary structure as well, which is comparable to what you see in proteins. But the sequence of bases is unique, and it might seem bizarre to you that with only 4 bases to choose from, it would be difficult, you would think, to have a really unique sequence of bases that would really carry that much information, but that's the way it works. You look at computers which work on zeros and ones. So that makes some of this a little bit, it gets easy to get lost in the basic simplicity of the structure if you don't realize that these are very, very large molecules for the most part. So the 3' hydroxyl group of one nucleotide bonds to the phosphate on the 5' carbon of the next nucleotide, as you've seen going on here. So let's see what that works here. The 5' carbon is bonded via a phosphate to the 3' carbon of the next one, and they're already moving in 2 different directions on you here. So these are called phosphodiester linkages, phosphodiester bonds. Terminators are terminated at one end. I'm just really summarizing what we've already talked about for a few minutes. These are terminated at one end by a free phosphate attached to the 5' carbon on the sugar of the corresponding nucleotide. What I mean by that is this over here. That's the 5' end. So there's a 5' phosphate attached to the 5' carbon atom on this nucleotide. Remember, I mentioned that the primes refer to the sugars, and we're not really talking too much about the numbering system of these things, of the bases, so we won't worry too much about that. So you know where the prime comes from. On the other end, it's terminated by a free 3' hydroxyl of a sugar. So if you look, this is if we look at this 4 nucleotide nucleic acid, and this is going to be a ribonucleic acid, the free 3' end, you see it just has the 3' hydroxyl here. The 2' does not involve itself in the formation of the nucleic acid in this polymer formation. It's just a 3' and 5'. In fact, in DNA, this 2' hydroxyl isn't even present. And we read from 5' to 3'. So if you go through your book, you're going to see this pretty much consistently. Again, when we talk about DNA, there's the complementary strands, the double helix. We have to modify that just a little bit, but not much. We've already seen how this works. Well, we've seen how the formation of the nucleoside by the condensation of the base with the sugar, and the condensation of the sugar of a sugar hydroxyl with the phosphate of another nucleotide is similar. You're removing this hydrogen here and a hydroxyl. Let me see we get this right. Okay, there's OH, H. You see it's not quite as clear the way this works, but you are removing a water molecule in this condensation reaction. So you're going from you're making this phosphodiester linkage by splitting a water molecule out of this assemblage. Well, out of the 2 nucleotides to form this assemblage. It's an esterification reaction. So to draw the condensed structural formula for the RNA dinucleotide formed by two cytidine 5' monophosphates. That's a mouthful, cytidine 5' monophosphates, but you should already be able to envision. Well, cytidine, you know that it's a pyrimidine, and you should know that there is a it's going to be an amino group and a carbonyl on there. We'll get to that eventually. This is how we're going to do this, though. Well, you want to draw this dinucleotide, so you're going to have. You want to put the we're going left to right. We're going 5' to 3' end. Okay, and so you have to connect the 3' hydroxyl group. So you line them up so that the 5' end, the 5' phosphate of one of the nucleotides, lines up conveniently with the 3' hydroxyl of the other nucleotide, and then you will connect those as we'll see. Okay, so here we have this is the completed structure here. So you see this is the 5' end. Okay, there's this phosphate is staying intact, it's not changing. The 5' end of the second nucleotide forms the phosphodiester linkage with the first one. So it's 5', 3', 5', 3', and then this one is, and then this one's going to go 5' to 3', and then this one's going to get attached to another 5', and then so forth. Think about this and just absorb it, because it's going to move in that direction all the time. Nucleic acids are really pretty uniform in doing this. Again, it's not really a lot different in principle than proteins, but here you're talking about a selection of only 4 nucleotides versus 20 amino acids. And nucleic acid sequence, as we've been talking about, from the 5' end to the 3' end, that's how you read it. So you start with the 5' phosphate end and just keep going all down the line here. So using this, writing this sequence with what we use, these capital A, capital G, capital C, capital T, and capital U, it would just be ACGU. And actually, there's these dashes here. The dash here, you really probably wouldn't necessarily need that, because this is really the beginning of the chain. But this could be, this of course could be inside a chain. We just cut it out using the right enzyme and take this piece, and we're studying it. But that's the way you write it, from 5' to 3'. And you're almost always going to see these. You're almost always going to see these written this way when you see it in a textbook. It's the way it's been done for decades. There are other shorthand ways of writing these, and I don't believe there's any. I don't think there's any of them in the text. Well, there actually is some other. The book has some of its own, but any other shorthands that are used are really pretty easy enough to understand. So, another learning check. In a nucleic acid, the nucleotides are joined by a fill-in-the-blank bond that joins the 3' group of the sugar to the phosphate group on the 5' on the next nucleotide. Well, if you've been listening, you know that I've been mentioning a certain type of bond between these nucleotides, and you'd remember that I said phosphodiester. It's more phosphodiester linkage. If you think of, you can think of the whole linkage as a bond, you can do that. But it joins the 3' group of one sugar to the phosphate group, 3' hydroxyl group of one sugar to the phosphate on the 5' hydroxyl on the next nucleotide. That's simply the way we did. This is a convention. Yeah, I mean, you could go from 3' to 5', I suppose, if we had decided to do it that way. But this is this convention, 5' to 3' does have some logic to it, in that nucleic acids generally are synthesized from the 5' end to the 3' end. In fact, they're all synthesized that way. Nucleic acid synthesis goes from 5' to 3' always. When we talk about DNA replication, then you're gonna see that causes some problems for the enzymes that are used, and requires a different set of enzymes when they're opening the the double helix to get into there and synthesize to what they call the daughter strands. But we'll get that in a couple sections. Another learning check here. As you can see, we're getting kind of to the end of this. This is a fairly simple section. In the nucleic acid sequence, CGAU, which base is at the free 5' phosphate end? You should know that. That's really all we're talking about in this particular section. That's the main thing, just the way these things are assembled, what they're put in these chains. So, which base is at the free end? We go left to right, 5' to 3'. So, left to right is from C through this, so it's going to be cytosine. So the answer should be A. And the answer that they give here is A. Cytosine is at the free 5' phosphate end. All right. This was a fairly simple section. Section 17.1 was a simple section as well. 17.3 is going to get a little bit more complicated, but it's short and it's not going to take very long. But then we're going to really start getting into 17.4. We're going to actually start getting into these things, doing some chemistry, or better yet, molecular biology. So it's going to ramp up in a hurry. So I'm leaving you with these two for tonight, 17.1 and 17.2, or whenever you're getting at these. You really need to know the simple parts. You really need to know the basics to begin with, because this is going to get very, very complicated. And chapter 18 is going to be pretty involved too, although it's going to have quite a bit different nature than nucleic acids. But we are really in the meat of this course right now. Biochemistry, molecular biology. Molecular biology is really all about the behavior of the genome, how it works. So I'm going to close here and upload this, and I'll hopefully see you tomorrow with a couple more videos. Thank you very much.